OK, the second encryption scheme that we'll see today is something called CTR mode. And again, we'll design it together and then analyze all of its properties. So this one is actually not based on block ciphers right away, but I think it's more based on the one-time pad. So if we go back to the one-time pads actually did have security as long as you didn't reuse this key. So remember, if you reuse the key, it's a 2-time pad, it's no good. But if every time you encrypt something, you use a different key, this is totally fine. You use a different key, you encrypt it with the plain text by XORing, and then you get the ciphertext. So what if I could do this, but I didn't have to generate new keys every single time? So that's our goal with this encryption scheme. I want to imitate this behavior, but I don't want to have to generate new keys every single time. So this is the first idea I need. The second idea I need is now I'm going to bring back the block cipher and remind myself that if the attacker doesn't know the key, this basically looks random. Remember we said that if the block cipher is secure, this output is indistinguishable from random. You might as well have dropped in the arrows in the permutation in here at random. So that means if the attacker doesn't know the key, which they don't, then this value is as good as random. The attacker has no idea if this was generated from the block cipher or by dropping in the arrows randomly. They cannot tell the difference. So this is random looking. It's not exactly random, like the key you generate here, but it's random looking. From the attacker's perspective, they think it's as good as random. So what if we use this and we combine it with this idea, and now we don't have to generate new keys every single time? So this is like a fusion of one-time pads and the fact that block ciphers are indistinguishable from random permutations. So we'll take these two ideas, we'll fuse them together, and we'll get something that looks like a one-time pad, but it's based on block ciphers, which is pretty cool. So we might need more randomness than just this one block. Remember, you want to be able to encrypt longer messages, multiple messages. So actually, I might need to use block ciphers multiple times. So if the attacker doesn't know the key, all of these outputs are as good as random. The attacker might as well think they're random. They can't tell the difference between this and actual random bits. So I will just run block cipher encryption as many times as I need. If it's a long message, I'll run this lots of times. I'll obtain lots of random outputs. And then I'll just use that output as a one-time pad. So whatever this output was, I'll take that output, which is right here. I'll encrypt it with the plain text, and I'll get the ciphertext. And then if I have more plain text, I'll generate more randomness, or random looking things, encrypt it by XORing with the plain text, and I get the ciphertext. So the top half of this picture is using block ciphers to generate random looking output. And the bottom half of this picture is just the one-time pad from before. So I've taken two ideas, and I fused them together to get a new encryption scheme. There's just one thing we have to do to finish up this scheme. We haven't actually told you what this input is. What do you actually input into the block cipher encryption? Well, we've already got the plain text down here and the ciphertext, so we don't have to write those a second time. So what do you put up here? What else is missing from this scheme that we could possibly put up here? Well, so far, this scheme seems deterministic. If I run the same encryption multiple times, I still get the same random output. So I'm missing randomness. And I haven't put anything here, so why don't we shove the randomness up there? That's what we do. So the final piece of the puzzle is to shove some randomness as the input to the block cipher. The only goal of the block cipher here is to generate random looking output. And one way to achieve that is to pass in some random input. So what we'll do is we'll pick a random number. Here it's called a nonce. It's just terminology. And we'll pass it into the block cipher, encrypt it with the key, and the result should be random. Now, if you use the same nonce every single time, then every single one of these outputs would be the same. And that's no good. You're reusing one-time pad keys. So we'll add a counter. So this is the nonce plus 0. This is the nonce plus 1. This one is the nonce plus 2, and so on and so forth, so that all of these outputs are different. And remember, block ciphers are random permutations, or they behave like them anyway. So if you change even a single bit, like the 0 becomes a 1, the resulting output should be totally different and unpredictable. So just because you change one bit up here, the resulting output should be totally different, and that lets us get lots of random looking output to use for our one-time pad. So So we've combined two ideas and designed something called CTR mode. And notice that the counter has to go up for every block so that this block cipher output is different. OK, so we built it. It's called CTR mode. CTR stands for counter, I guess because there is a counter in this scheme. And it works like we described. So you take a nonce. That's a randomly generated value. You flip a bunch of coins to get a nonce. And you do it once for every encryption. Once you have the nonce, then you take the nonce, you append 0 or add 0. It's up to you. And then you encrypt it with your key. You get some padding output or some random looking output. That's your pad for the one-time pad. You XOR it with the plaintext. You get the first chunk of ciphertext. If you have more plaintext, well, no problem. Take the nonce. Now add 1. Pass that into the block cipher with the same key. You get a bunch of more random looking output. XOR that with the plaintext. You get the next block of ciphertext. And you repeat this as much as you need until your whole message is encrypted. So that's basically it for how counter mode works. And remember, you are using the same key every single time. If you use different keys, you've defeated the point. Remember, our whole goal of avoiding one-time pads was to avoid having to use different keys every single time. So we are using the same key here. And the reason why all of these outputs is different is because that counter keeps changing. So the key is the same. The attacker doesn't know it. The counters is what makes this output different. So there it is again in English. You split the message up, and you generate random-looking blocks of output. And then you encrypt each plaintext block by XORing it with the corresponding block cipher output.